In this lesson, we're going to learn about logarithms. Now, mathematics is a language, and just like any language, when we're learning to read and understand mathematics, we need to learn what different mathematical notations mean. Mathematicians developed logarithms to help us solve for exponents. In fact, logarithms represent exponents. Let's take a look at a few examples of basic logs before we get into the formal definition of logarithms. So we would read this as log base 6 of 36. Now, a logarithm represents an exponent. So if you see a logarithm, you know that you're looking for an exponent. What exponent are we looking for? Well, the way we read this is that we're looking for the exponent that we need to put on the base 6 to get the answer 36. I'll say that one more time. What exponent do we need to put on 6 to get 36? 2. So the value of this logarithm is 2. Again, a logarithm represents an exponent, and in this case, when we're trying to find this log, we're trying to find the exponent that we need to put on 6 to get 36, and that is 2, because 6 squared gives us 36. Let's try another one. Remember that a logarithm represents an exponent, so if you're asked to find the value of a log, you're really looking for an exponent. What exponent are we looking for here? We're trying to find what exponent do we have to put on 2 to get 8? 3. So the value of this logarithm is 3. Again, when you're computing a log, you're finding the exponent, and for this log, we were finding the exponent we needed to put on 2 to get 8. And that exponent is 3 because 2 cubed gives us 8. Let's try another one. We see a log, so that means that we're looking for an exponent. What particular exponent is this log asking for? Well, we're trying to find what exponent do we have to put on 3 to get 81? 4. So the value of this logarithm is 4. Because 4 is the exponent, we have to put on 3 to get 81. Now, these are the logarithms that we just discussed. We call this form logarithmic form. Any expression written in logarithmic form can be rewritten in exponential form. Logarithmic form and exponential form are equivalent. They just present the information in two slightly different ways. Remember, on the previous page, we said that log base 6 of 36 is equal to 2 because 2 is the exponent that we need to put on the base 6 to get the answer 36. I'm going to label the pieces here. 2 is the exponent that we need to put on the base 6 to get the argument 36. And the argument is another word for the answer. Now let's rewrite this in the equivalent exponential form. Remember, we said that 2 is the exponent we need to put on the base 6. So we can say 2 is the exponent we need to put on the base 6 to get the answer 36. These mean the same exact thing. This means that 2 is the exponent we need to put on the base 6 to get the answer 36. This says the same exact thing. This says that 2 is the exponent we need to put on the base 6 to get the answer 36. And if we label the pieces here, 6 is our base, 2 is the exponent, and 36 is the argument, which means the answer. Let's take a look at this example. Log base 2 of 8 equals 3 means that 3 is the exponent that we need to put on the base 2 in order to get the argument, or in other words, the answer 8. Let's write this logarithmic form in its equivalent exponential form. We said that 3 is the exponent that we need to put on the base 2 to get the answer, or the argument, 8. And let's label the parts. 2 is the base, 3 is our exponent, and 8 is the argument. And lastly, log base 3 of 81 is equal to 4 because 4 is the exponent that we need to put on the base 3 to get the answer, or in other words, the argument 81. Let's write this logarithmic form in its equivalent exponential form. We said 4 is the exponent that we need to put on the base 3 to get the answer, or in other words, the argument 81. And let's go ahead and label the parts of the exponential form. So the base, the argument, and the exponent are organized in a slightly different way in the logarithmic form in comparison to the exponential form. But while these two forms present the information in a slightly different way, they mean the exact same thing. So anytime you have an expression written in logarithmic form, you can always rewrite it in exponential form, or if you have an expression written in exponential form, you can always write it in logarithmic form. Let's take a look at example 1 here. Example 1 asks us to solve for m. What is m? Remember, a log is always equal to an exponent. So m is our exponent, and m is the exponent that we need to put on the base 3 to get the answer or the argument 9. Now you might be able to find m mentally, but especially when the problems get more difficult, when you have a problem written in logarithmic form, it can be helpful to rewrite it in exponential form. So let's practice doing that. We said that m is the exponent that we put on the base 3 to get the answer or the argument 9. And let's label the parts of our exponential form. So notice, while the logarithmic form presents the information in a slightly different way than the exponential form, they both ask the same question. The logarithmic form is asking, what is the exponent m? We need to put on the base 3 to get the answer 9. Let's write that using words. The logarithmic form is asking, what is the exponent m that we need to put on the base 3 to get the answer 9. Notice we can use those same exact words for the exponential form. The exponential form is asking, what is the exponent m that we need to put on the base 3 to get 9? That matches exactly what we wrote here for the logarithmic form. So whether we write the expression in logarithmic form or exponential form, either way, the answer is that m is equal to 2. Because 2 is the exponent, we need to put on the base 3 to get the answer 9. Or here we can see 2 is the exponent, we need to put on the base 3 to get the answer 9. Let's take a look at example 2. So remember, a logarithm is always equal to an exponent. So this is asking, what is the exponent, w, that we need to put on the base 5 to get the argument 125. Let's write those exact words right here. What is the exponent w that we need to put on the base 5 to get 125? Let's practice rewriting this log in its equivalent exponential form. Again, w is the exponent that we need to put on the base 5 to get the answer or the argument 125. And let's label the parts of our exponential form. Now we used these words to describe this logarithmic form. We can use these exact same words to describe this exponential form. What is the exponent, w, that we need to put on the base 5 to get 125? And the answer for this expression, whether it's written in logarithmic form or exponential form, is that w is equal to 3. Because 3 is the exponent, we need to put on the base 5 to get the answer 125. Or if we read it in its logarithmic form, 3 is the exponent, we need to put on the base 5 to get the answer 125. Logarithms are used a whole lot in the real world. Logarithms are used for things like modeling the magnitude of an earthquake or predicting earthquakes. They're used to model the pH level in solutions. They're used to model radioactive decay and to estimate the age of organic materials, which is called carbon dating. They're used to measure and model sound. They're used to measure and predict population growth. And they're even used to model interest, stocks, and currency. Now, I'm going to copy this logarithm and this logarithm onto a separate sheet of paper, and then I'll show you a nice trick that can help you convert from logarithmic to exponential form. So a quick trick we can use to convert from logarithmic form to exponential form is we can start by bringing down the base, 3. Now in logarithmic form, the base is written as a little subscript. In exponential form, the base is written as just a normal sized number. After we've brought down the base, then we switch the next two values. So we put the 9 over here, and we put the m over here. And when written in exponential form, the m is written as a small superscript like shown here. And then we can add our equal sign. Let's try that little trick over here. So we start by bringing down the base. And again, in logarithmic form, the base is written as a small subscript. In exponential form, the base is just written as a normal sized number. And then we switch the next two values. So we put the 125 on the other side of the equal sign, and we write the W as a superscript right here. Next, we're going to write the general definition of a logarithmic function. So if this is our log, as it says right here, we would read this as log base A of x is equal to y, where A is the base, x is called the argument, and whatever your log is equal to, that represents your exponent. So y in this case is the exponent. Anytime you have something written in logarithmic form, you can always rewrite it in an equivalent exponential form. So like we've been practicing, in exponential form, we start with the base, which is a. Then we take a and raise it to the exponent, which is y in this case. And then in exponential form, we set that equal to the argument, which is x in this case. So let's practice converting from logarithmic form to exponential form. Now, I want to emphasize that whether your problem is written in logarithmic form or exponential form, both forms are stating the same thing. For example, remember a log is always equal to an exponent. So in this case, c is our exponent. So this logarithmic form is stating that c is the exponent that we put on the base 7 to get the argument or the answer 20. So let's use our trick to convert this to exponential form. Our trick says we just need to bring down the base, so we'll bring down the 7, and then we switch the next two numbers. So we'll put the exponent, or the c, over here, and we'll put the argument 20 over here. Notice this exponential form states exactly what we wrote over here. It states that c is the exponent we put on the base 7 to get the answer or the argument 20. Let's go ahead and convert this logarithmic form to exponential form. Now, if you want to use this trick, start by rewriting this logarithmic form so that we have the log on the left. And to do that, we can just swing these around the equal sign and write this as log base 2 of 16 is equal to 4. Now, before we use the trick, let's just use words to explain what this is saying. Remember, a log is always equal to an exponent, so 4 is our exponent. So this is saying 4 is the exponent we need to put on the base 2 to get the answer or the argument 16. Now let's write this in the equivalent exponential form, and we'll use our trick. So we'll start by bringing down the base, which is 2, and then we can write our equal sign, and then we can switch the next two numbers. We'll put the 16 over here, and the 4 is our exponent, so we'll raise the 2 to the 4th. Now, I encourage you to pause the video and go ahead and try to rewrite problems 5 and 6 in exponential form. When you're ready, you can play the video to check your answer. So if we use our trick here, we'll bring down the base, and then we switch the next two numbers. Now, before we use the trick to convert this to exponential form, let's rewrite this so we have the log on the left. Okay, now let's bring down the base, and then we can write our equal sign and switch the next two numbers. On the previous page, we were given a logarithmic equation and we were asked to rewrite it as an exponential equation. On this page, we're going to practice going in the reverse direction. We'll start with an exponential equation and we'll rewrite it in logarithmic form. Let's start by identifying the base, the exponent, and the argument. The 3 is our base, y is the exponent, and 16 is the argument. To write this in logarithmic form, we'll start by writing log. Then the base is written as a subscript on our log. Next, we put the argument right here, and we can write our equal sign, and the log is always equal to the exponent. So we'll set the log equal to the exponent y. Now, the trick that we learned on the previous page works when you convert from logarithmic to exponential form, but the trick also works in the reverse direction if you're going from exponential form to logarithmic form. So let's see how we could have used that trick here. Just like we did on the previous page, we start by bringing down the base, so we would have brought down the 3, and then we switch the next two numbers. So we would put the y over here and the 16 over here. Let's try using that trick for problem number 8. So if we want to write this in logarithmic form, let's start by writing log. Then we bring down the base, which is 2, and when we're writing it in logarithmic form, the base is a subscript. Then we can write the equal sign, and then we'll switch the next two values. So we can put the argument or the x here, and this exponent goes over here. Let's try number 9. Now, before we use this trick, we have to make sure that our exponential equation is written so that you have your base and your exponent on the left, just like we had here. So let's swing this around the equal sign to rewrite this as 6 to the x is equal to 216. Now that we have the base and the exponent on the left, now we can use our trick. So to write this in log form, let's first start by writing log. Next step, we bring down the base. So the base, which is 6, can be written as a subscript. Then we can write the equal sign, and then we switch the next two values. So the x goes over here, and the argument, the 216, goes over here. Go ahead and pause the video and try problems 10 and 11. After you've tried those problems, you can play the video to check your answer. Next step, we're going to learn how to evaluate logarithms. To evaluate a logarithm, that means you're calculating the exact value of the logarithm. And in order to evaluate, or in other words, find the exact value of a logarithm, we're going to follow these 3 steps. And for the first problem, I've typed those steps out for us to see. So we want to find the value of this logarithm. Now remember, a logarithm is always equal to an exponent. What particular exponent is this log asking for? Well, we're trying to find the exponent. We need to put on the base 3 to get the answer 729. Even though you might be able to solve this logarithm very quickly without using steps 1, 2, and 3, it'll be helpful to practice steps 1, 2, and 3 to prepare us for the more complicated problems that we'll soon see. Step 1, we're going to set our logarithm equal to some variable, whatever variable you want, something like x or y or z. So I'm going to write our logarithm, log base 3 of 729, and set it equal to any variable we want. I'm going to use y. So what we've done here is we've said we're trying to calculate the value of the log, and we don't know the value at this point, so we're saying that this logarithm is equal to some unknown value y. Now, let's think through this. We would read this as log base 3 of 729 is equal to y. Now remember, a logarithm is always equal to an exponent. So what are we trying to find here? What is the exponent y we need to put on the base 3 to get the answer 729? So in step 2, we're going to rewrite our logarithmic equation as an equivalent exponential equation. And we can use our little trick to do that. So our trick says, bring down the base. So 3 is our base. And then we can write our equal sign. And then we'll switch the next two numbers. Our exponent y goes on our base, and 729 goes over here. So now we've written this in exponential form. We're still trying to find what is the exponent y we need to put on the base 3 to get the answer 729. Now we've got an exponential equation here, and we learned in chapter 8.2 how to solve exponential equations. The first step for solving exponential equations is we want to write both sides with the same base. Now to do that, we could rewrite 729 using base 3. 729 can be rewritten as 3 to the 6th, and then let's bring down our 3 to the y. So now we've rewritten our problem so that both sides have the same base, 3. Once we've done that, in order to solve our exponential equation, the last step is we just need to set the exponents equal. So we'll set y equal to 6. Now, in order to answer our problem, what does y represent? Well, y is the value of our logarithm. So we can say our log, the log base 3 of 729, is equal to 6. Let's say in words what this means. This means that 6 is the exponent that we need to put on the base 3 to get the answer 729. Let's try a problem that's a little bit more difficult. And we'll follow these same 3 steps. Step 1, we're going to set our logarithm equal to a variable. I'm going to again use y, but you can use whatever variable you want. Now, what are we trying to find? Well, a log is always equal to an exponent, so y is an exponent, and we're trying to find what exponent y do we need to put on base 2 to get the answer 1/8. So step 2, we're going to write this in exponential form, and we can use our trick to do that. Let's start by bringing down the base, which is 2, and then we can write our equal sign, and then we'll switch the next two values. So we put the y, the exponent, over here, and the 1/8 over here. Now we've rewritten our logarithmic equation as an exponential equation. Step 3, we want to solve the exponential equation. And remember, the first step for solving exponential equations is we're going to write both sides using the same base. Now that's a little bit tricky because we have this fraction over here. But let's just pay attention to the 2 and the 8. And let's start by thinking, can we rewrite 2 and 8 using the same base? We can, because we can rewrite 8 as 2 cubed. So let's rewrite the fraction as 1 over 2 cubed. So we've rewritten the 8 as 2 cubed, and now let's bring down the 2 to the y. Now we want both sides written using the same base, but when solving exponential equations, we don't want a fraction here. Now let's just quickly review negative exponents. We typically don't like negative exponents. So if we see a problem like this, we usually like to write it without negative exponents. And to do that, we'll take this and move it to the denominator and write it as 1 over 2 to the positive 3. Now usually we don't like negative exponents, so we'll rewrite it like this using positive exponents. But for the particular problem that we're working on, negative exponents are actually going to be helpful. So we're going to start off with this, and we're actually going to rewrite it using a negative exponent. So we're going to pick this up and move it to the numerator, and that's going to make our exponent negative. So let's pick this up and move it to the numerator, and that will give us a negative exponent, 2 to the negative 3, and then we'll bring down our 2 to the y. Now we've written both sides using the same base, and we've gotten rid of this fraction. Last step is we want to set the exponents equal. So we'll set y equal to negative 3, and we've got our answer. Let's just remember what y represents. Y represents the value of this logarithm. So we can say log base 2 of 1/8 is equal to negative 3. What does this mean? This means that negative 3 is the exponent we need to put on 2 in order to get the answer 1/8. Let's try one more similar example. So let's suppose we're asked to find the exact value of this logarithm. Step 1, let's set the logarithm equal to some variable. And I've set our log equal to y. Now let's just pause for a second and ask ourselves, what are we trying to find? Well, y represents an exponent, and we're trying to find the exponent y that we need to put on base square root of 2 to get the answer 64. Step 2, we're going to rewrite our logarithmic equation in exponential form. So square root of 2 is our base, y is our exponent, and 64 is the argument, which we place here. Now that we've written our problem in exponential form, let's move on to step 3. In step 3, we want to solve our exponential equation. The first step of solving an exponential equation is to write both sides using the same base. Now this is a little bit tricky because of the square root, but let's ignore the square root for just a second. And let's look at the 2 and the 64. And let's ask ourselves, can we write both sides using base 2? We can. We can rewrite 64 as 2 to the 6th. And then let's bring down the square root of 2 raised to the y. Now let's look back at the previous problem. When you're solving an exponential equation, the goal is to get both sides to have the same base, and you don't want any fractions, so we had to rewrite this without a fraction, and we also don't want any radicals, so we need to rewrite this without the square root. How do we do that? Well, if we remember back to the 6.1 video, we learned that anytime you have a radical, you can rewrite that radical using fractional exponents. And we can rewrite the square root of 2 by taking 2 and raising it to the 1/2. So the square root is equivalent to raising to the 1/2. So the square root of 2 and 2 to the 1/2 are equivalent. And this is supposed to be raised to the y, so we have to make sure we're still raising this to the y, and then this is equal to 2 to the 6th. We want to simplify if we can, and if we remember our rules of exponents tell us when you raise an exponent to an exponent, you can multiply those two. So let's rewrite this as 2 to the 1/2 times y, or in other words, 1/2 y, and then we'll continue bringing down the 2 to the 6th. Now we've successfully written both sides using the same base, and we got rid of that messy radical. Next step, we set the exponents equal and solve. So let's set the exponent 1/2 y equal to this exponent 6. And to solve for y here, we could either divide both sides by 1/2, or instead of dividing by 1/2, we could instead multiply by the reciprocal, 2 over 1. And I think I'll do that. So I'm going to multiply by 2 over 1, and then by 2 over 1. The reason we do that is because when you multiply two reciprocals, you get 1. So this leaves us with 1y, or y, is equal to, and 6 times 2 will give us 12. Now we've solved for y, but what did y represent? Y represented the value of our log. So for our final answer, we can say that the log base square root of 2 of 64 is equal to y, which is 12. Now let's use words to describe what we just found. We found that 12 is the exponent that we need to put on the base square root of 2 to get the answer 64. Now there's two types of logarithms that appear in the real world more often than any other type of log. These two types of logs appear so often that one is called the common log and the other is called the natural log. The common log is any log with a base of 10. So we'll represent that as log base 10 of x. So again, when you have a log with a base of 10, we call that the common log. Log base 10 is so common that mathematicians have created a condensed way of writing it. Log base 10 of x is written in condensed form simply as log of x. So if you see a log with no base, the implied base is always 10. So for example, if you see log 5, there's no base written here, and if there's no base written, it's assumed that the base is 10. So this means log base 10 of 5. Let's suppose you saw log of z. Since there's no base, we can assume the base is 10. Log z means log base 10 of z. The next type of log that is used a lot in real-world applications is the log with the base e, which we'll write as log base e of x. Any log with a base of e, we call the natural logarithm. We call this the natural logarithm because it has so many applications in nature. For example, log base e can be used to model growth and decay in plants and animals. Because log base e is used so often in the real world, mathematicians have developed a condensed way to write it. Instead of writing log base e, we write ln, which comes from its name, the natural logarithm. So log base e is replaced with ln, and then we still write the argument x. So let's practice that. Let's suppose we have the natural log of 7. What does this mean? Well, ln represents log base e. So ln can be replaced with log base e. Let's try one more. Let's suppose you see the natural log of 40. Again, ln means log base e. So you can always replace ln with log base e. Let's take a look at these last two examples together. We're asked to change the logarithmic equation to an equivalent exponential equation. Let's start with this one here. Now, there is no base written. So remember, if we see the log written with no base, we can always assume the base is 10. So I'm going to rewrite this as log base 10 of 1000 is equal to 3. Now that we've identified our base, now we can use our trick to write this as an exponential equation. To start, let's bring down the base, 10, and then we can write our equal sign, and then we'll switch the next two numbers. We'll put the 1000 over here, and the 3 is our exponent that we put on the 10. Let's take a look at this problem here. So here we have the natural logarithm of 9 is equal to x. So to write this log in exponential form, we have to identify the base. Remember, if you see ln, that just means log base e. So we can always rewrite ln as log base e. And then we'll copy down the other pieces, the argument, which is 9, and the exponent, which is x. Now that we've rewritten it so that we can clearly see the base, now let's write this in exponential form. We bring down our base, which is e, and then we can switch the next two values. We'll put the 9 over here and the x over here. So here's the exponential form. E to the x is equal to 9.